Okay, so we're back one last time. This is the final bit we're going to do for the data analysis. What we've achieved so far, we've got our line of best fit with a gradient, and the gradient is our experimentally determined measure for density of our metal samples. Now, it might be a good estimate of the true value. It might not. So, how good of an estimate, experimentally determined value for density, how good it is going to depend on our uncertainties in measurements, and we've represented them using our error bars. Now, how do those measures of uncertainty in mass and volume, how do they translate to error in density? So this is where a graphical approach to estimating uncertainty in the gradient of this straight line fit is important, and we're going to run through this as a bit of a concept. So we need to get some information, some things set up on our spreadsheet. We need to know some coordinates that will produce a line that will give us the most minimum gradient. And we need so we need some x coordinates and some y coordinates and 2 points to make a straight line. Point 1 and point 2. So looking like that. And we're going to construct our points that we need. So copy. We also would like to know what line produces the most maximum gradient. We call max gradient section, and to produce a line we need at least 2 points and of course x and y coordinates. Our x coordinates are our volumes and our y coordinates are our mass. So this allows you then, if to having two lines, one that is the absolute most maximum gradient, looking like that a bit, that will be one edge of a boundary, and another line that produces the most minimum gradient, might be looking a bit like that, will give us another edge of a boundary, and we get a bit of a tunnel. And within this tunnel is an allowed range of uncertainty that our line of best fit can fit between. Okay, that gives us some measure of uncertainty in the gradient. All right, so the first point, we need to consider it as the most lowest point on the graph. So to get that, we need some measure of volume. Our first measure of volume, which is this one. Okay, once we've got this one, we have to ask ourselves, well, what is that one? Now, what I was talking about, two gradients, one that gives you a minimum gradient, one that gives you a maximum gradient. You need to refer to this little chart we have here. This is an example of a scatter plot with some error bars, and we've got 1, 2, 3, 4 points labeled. And the notation there I'll explain in a second. But the red dots, if I connect them up in this manner, then what we obtain is a line that will in fact have the most largest gradient, and any other line within as long as they fit within the error bars will be a less gradient. So if it was down here, it's a small gradient. That corner, it's a little bit bigger, but this gradient, this corner over here will have the largest possible gradient. Okay, and the same applies for a line running between two other points. So if I start from this point and connect a straight line to this point over here, now I've got a line with a gradient that is the most minimum gradient, okay? And each point fits precisely between each error box, as defined by a horizontal and vertical error bar. The line will pass through each point within the error box, so it's valid, and that will give us the most minimum gradient. The line of best fit will be somewhere in between, and the region that the maximum gradient line and the minimum gradient line make produce like a bit of a boundary, a bit of a measure of uncertainty. Alright, so we need to be able to produce those lines on Excel, and to do that we have to draw on, set up these coordinates, find these coordinates and plot them as a scatter plot so we can connect with a line. First point over here is a volume quantity, and we have to subtract the error in volume. This one is a mass, and we have to add the error in mass, okay, to get this maximum point. And so we're going to keep flicking back to the screen so we know what we need to do to each coordinate to make sure we end up with finding the right points. So back to here. First, let's do the minimum gradient line. Point 1 is the most lowest point. Point 2 is the most highest point. So point 1, to get the x coordinate, which is your volume, we have to most minimum gradient, which is the red. We have to find our volume, and we subtract the error in volume. Let's do that. So equals. Now let's get our volume quantity. It's this one. And we're going to subtract press subtract button so it appears like that, subtract the error. Now remember, this is percentage error, this is absolute error. That's actual quantity of error in meters cubed. So we're going to subtract that error because this one corresponds with this one. Okay. Now let's just adjust that, and we get there we go. There's our value. Okay. The y coordinate is going to be, sorry Sarah, I'm not talking to myself. Teachers. Alright, the y coordinate's going to be, now for that point, let's flick back to the diagram. Y coordinate's going to be the mass plus the error in mass. So let's get the mass for point 1, which is this top point up here, mass plus the error in mass, this one. Okay, so there's our first point. Okay, let's do the second point. Second point for our minimum gradient is our red line, which is up here. This is our second point. So we have to get our volume quantity. Now this is the volume quantity. The second point we need to find is the most largest volume and the most largest mass. The one's way up here, so we have to identify them. We take the volume quantity and we add the error, and for the mass we take the mass quantity and we subtract the error. So next we're going to take the volume quantity. The most largest volume is going to be this one, 7.5. We take the volume quantity and we add or subtract. We're going to add, yep, we're going to add the error, which is 1, 2, 3, 4, fourth one in the list. Okay, let's adjust the decimal places so we can see it. Good. And for our mass, we have to take your largest mass and we subtract the error. Okay, so take the mass equals the largest mass is going to be this one, the fourth one. And we subtract the error. Spot on. Okay, so there's our minimum gradient line. before we plot it, let's do our maximum gradient line now. So the maximum gradient is the blue line. Point 1 down here starts with volume plus the error, mass subtract the error. So point 1, the x value, the volume plus the error. Alright, the most minimum volume, which is the first one here. And we plus the error. Yep. Okay, so volume plus the error. Now mass subtract the error. So come to the same point, point 1, mass, and we subtract the error. Beautiful. Now point 2. Point 2 is going to be way up here. There's point 2 for the maximum gradient line, so volume subtract the error. So let's grab the volume, and the most largest volume for point 2 is this one, so volume, and we subtract the error, not the percentage error, but this one down here, the absolute error. Okay, and finally our mass quantity. For this point, it's the mass, largest mass plus its error. So each time we're doing this, I'm putting an equal sign in for my formula. Alright, so grab the mass, which is this one, the largest one, and we plus the error. Voila. Thank God for that. Now let's get a scatter plot of this data. So to do that, come to our chart. Now we want to add. We want to add some data series. So if you click on the original scatter points there, like so, click, and we go to data. No, we go to design, and select data. Good. So under this, there's our original series, that's our measures. Now we're going to add. We need to add a series. We need to add some x values. So let's put the x values in of our first line. Add the x values, or x value. So the minimum gradient line, that's our x value, and that one's our x value. Point 1 to point 2. And corresponding y values from point 1 to point 2. Hit OK. Alright, so here we go. Hit. So that's series 2, that's going to be our min gradient line. While we're here, let's add now the points for maximum gradient line. So x values there's their x values, point 1 to point 2, and y values, point 1 to point 2. Okay, and there's our 3 series. We hit done, and now we can see the red dots connect to make a minimum gradient, and the green triangles are going to connect to make a most maximum gradient, just like we wanted. Alright, let's put a line between those two. Add a tread line. We want it now. This is important because we've produced these lines that have a minimum gradient and a maximum gradient. Now we actually want to know, well, what are those gradients? What is the most maximum gradient? What is the most minimum gradient? So we need to see it as an equation. And don't worry about the r² value, just the equation. So we can read the actual gradient value. There it is. So there is our most maximum gradient. No, most minimum gradient. And before we get confused again, whether it's the most maximum gradient or minimum gradient, joining the two red dots, we better label it. So min grad. That now I'm not going to make the mistake. Alright, let's do the same with green triangles. So add tread line, and we have we need equation. Alright, there it is, the line with the most maximum gradient, and let's label that home max gradient line. Okay, superb. And you can see it's the gradients are ranging from 10,600 down to 6,400, and our 8,200 is in the middle, in between. Perfect. And we can see the line of best fit passes nicely right in the middle. Spot on. Okay, it's a very good set of data, very good fit. The error bars are a healthy size so we can clearly see what's going on. And what's another important factor, every single line that we've added, all our tread lines, reside within each point. Okay, within the box of each point, and that's fundamental. Okay, so from there let's come to now some information, and let's see how we're going to get the error, the final error on our gradient. So we've got a measure of uncertainty for our density of our metal pipe. Okay, now so we got our gradient, line of best fit, maximum and minimum gradients, and we did that because we really want to know what's the uncertainty in our gradient measure. How good is our experimentally determined value for density of our metal pipe? So we use this rule. We take the maximum gradient, we subtract the minimum gradient, get a difference, divide by 2. So from that, reading from the graph, we had this. There's our maximum gradient, there's our minimum gradient values, we subtract, get a difference. We end up with approximately 2,100 as a gradient value. That is a density value, an error for density. So our final part of our experiment is in our discussion and our presentation of results, we have to present our experimentally determined value, our density of our steel pipe. So there's our gradient. Now we've just rounded off to only have 2 significant figures, and so you don't need to go into too much value with decimals. Just keep only up to 2 significant figures. 0 isn't considered a significant figure. And we then ask ourselves, well, is this a valid result? If I'm hired by a company to determine the density of a new super alloy that's going to revolutionize, the industry and all of infrastructure in a major city, then I better be pretty damn good with my specs on this material, and it's got to be, quite valid results. Am I going to get the big bucks for this experiment? Well, what is the percentage error? Is it too big? Is it too small? Generally, a company would have a level of tolerance on their what would they considered valid results from their experiments. Some high-end companies might expect maybe 1, 2, 3, up to 5% tolerance. Others might be 10% tolerance. What percentage of error is 2,100 out of 8,200? 25%. That's pretty laughable. I would get fired if I was getting paid for doing this. Hello. So I want you to then consider, why is it 25%? Why is our percentage error such a significant value? And I've actually fudged the figures somewhere in our spreadsheet. Somewhere to do with an estimate for error for one of our quantities. Can you figure it out? It's hidden there somewhere, and that would be a good explanation as to why we have such a huge error. Okay, I think we're done.